3, this is all about solutions. If you want to put it at the top of your page here, aqueous solutions, this is all about solutions in this unit here. A solution, of course, some definitions you want to know. A solution is made up of a mixture of a solvent, at least one solute. So when you think about solvents and solutes, you think about solids usually, and water, okay, is an option. When you take sugar and you put it into a coffee, for example, we would say sugar is the solute. The solvent in that case would be water, okay, or coffee, basically. That would be an example. Solutes and solvents can be liquids, gases, solids. It doesn't matter what state those are in, all right? For example, hydrogen chloride is a gas. We pump it into water, so hydrogen chloride, even though it's a gas, is considered a solute, and we pump it into the solvent water to make hydrochloric acid, okay? An aqueous solution. We are going to focus on aqueous solutions this unit, okay? All our solutions are going to be based in water for the most part, okay? So we're going to use water as the solvent, all right? Is any solution where water is the solvent? Make sure you know that, aqueous solution. Quite often you will see this little abbreviation for aqueous, AQ, which basically just means that. It means that it's been put into water, okay? All aqueous solutions are transparent and may be colored, so might have a red color, a blue color, or they might just be clear, colorless, okay? Electrolytes. Electrolytes are soluble compounds which conduct electricity when dissolved, okay? Make sure you know that. When we're going to talk about electrolytes later on, like for example, Gatorade and Powerade and all that stuff, we'll talk about that stuff. Electrolytes are soluble compounds which conduct electricity when dissolved. All soluble ionic compounds are electrolytes. Acids are also electrolytes. Those are your electrolytes, okay? When you put those types of compounds into water, you get plus and minus ions like you would in a battery, plus minus. And those are what's able to conduct electrical current, okay? Electricity is conducted from one free ion to another. If you can't remember that, at least remember what the non-electrolytes are. Non-electrolytes do not conduct electricity at all when dissolved, okay? What's an example of a non-electrolyte? Molecular compounds are non-electrolytes. Molecular compounds. And basically, if you think about molecular as not an electrolyte, we think about what's the other options. Ionic compounds, and well, acids kind of fall into that category a little bit. We'll talk about that in a second. Acids also are electrolytes, okay? Molecular not, everything else yes, okay? All right. So some definitions, those definitions are very important. We'll use those throughout the semester, or obviously next year too. When a solid dissolves, individual particles separate from each other and spread out in the solution. That happens with no matter what kind of substance you have. When you put something into water, it breaks up and it kind of dissolves, if you want. In some cases, not all cases. I guess there are some things that stay together, but with soluble kinds of compounds, they break up and they break apart from each other, okay? The first one we're going to talk about, these next three definitions are very, very important, okay? We have to know what these are called because I'm going to refer to them over and over again. You'll probably have a quiz on them at some point. Separation is the first one. You have to know that separation is for molecular compounds. Okay? Separation is the term we give to molecular compounds. It is the spreading out of individual molecules in water. Okay? When you take, for example, sugar. I got some questions for you now. You're going to take some sugar. In fact, we're going to keep this very simple. We're going to take 1 grain of sugar. You know when you put your finger in the packet and you take out 1 grain of sugar? Yes? Okay? And you hold it on your fingertip. Question. How many molecules of sugar are on your fingertip right there in that 1 grain of sugar? Give me a number. Give me an answer. What do you think? Is there 1 on that 1 grain of sugar? No. How many? I'll give you a hint. It starts with L. Lots is the correct answer. Okay? I don't know exactly how many. You know what? We could figure it out someday. Maybe I need to do that. We'll put it on a scale. We'll weigh that 1 gram of sugar. We'll convert it to moles. We'll convert it to molecules. How's that? Yeah? I could tell you. Let's say, for example, I'll just throw a number out there. Let's say there's a million in that 1 grain of sugar. There's probably a little bit more than that. Let's say there's a million on your fingertip. By the way, a million on your fingertip, let's think about that. Molecular compound, there's a million of all linked together. What do you know from unit 1 that kind of would tie that all together there for you? What's holding them together? Yep. Could be London forces. Could also be, dipole. Yeah, those are temporary dipoles. Could be dipole-dipole. Could be hydrogen bonding probably as well, right? Could be any of those 3. I'd have to actually look at the structure, yes, and decide on that. Now, you can look here, C12H22O11, and you could say, is there London forces? Well, absolutely there is, because London forces are based on size and shape, right? So there's absolutely London forces there. Is there dipole-dipole? I'd probably say, yeah, there is, because I doubt that that's going to be very symmetrical when it's all done, okay? And that's just maybe something that maybe only I know, but probably not going to work itself out nice and evenly with all those carbons, hydrogens, and 11 oxygens, not an even number. And then the third thing I say is there hydrogen bonding. And there's a very good chance that there's probably some hydrogen bonding there as well, because you do have a lot of O's and a lot of H's. So there's probably a good chance somewhere in there's an O bonded to an H. In fact, there could be a lot of them. I don't know. Okay? So it could be hydrogen bonding. What else do you know about the intermolecular forces, though? Hint, hint. What else do you know about these intermolecular forces from Unit 1? Look. They're what? Regardless of what it is, they must be S, T, yes. Why? There's lots, yeah. Why are they strong forces? No, there is a lot of them. And they're all connected together. Why? How do I know they're strong? It's a solid, right? It's in solid form. So they must be hooked together pretty well, right? Because remember, if they're a little bit weaker, it's a liquid. If they're weaker yet, that's gas, right? Intermolecular forces, remember, are 100% responsible for states, solids, liquids, gases, yes? So that's something from Unit 1 we'll need to review a little bit, yes? All right, so we got this 1 grain of sugar. Let's say it's got 1 million molecules of sugar, and they're all linked together. They're all in solid form. They're linked up nicely. I dump it into water, and what happens when I take that 1 grain of sugar and I dump it into water? What happens? It disappears. It's magic. It dissolves. Eh? Those are all good terms, and you know what the best term is? It undergoes the process of separation. It breaks apart from each other. Water pulls that molecule apart, and we get now still molecules of sugar. Okay? We usually put a little AQ with those to represent that basically, okay, it's in water now, first of all, those molecules of sugar. Are they still together? No. They've broken up into, instead of 1 million all linked together on your fingertip right here, instead of 1 million right there, now you got 1 million, but they're all spread out throughout the solution. And you can't see individual molecules of sugar, right? Can't see one molecule of sugar, too small. So now you know that you still have 1 million there, but they're now all spread out, okay, into individual molecules of sugar. So it tastes like sugar if you drink the water, you know, if you had a small enough amount, of course, or if you put enough sugar in, grains of sugar in, still tastes like sugar. You don't see the sugar, but there's still molecules of sugar in there. They're just independent of one another now, right? Those intermolecular forces were broken. So if we had 1 million, for example, up here, we now have individual molecules down there. Okay? So instead of them having all linked together, now they're individual. That's the process of molecular compounds, and that's called separation. Okay? Once again, okay, if you put too much sugar in, guess what? Water can't break it all apart. There's not enough spaces between the water for it to basically break that apart, and it becomes oversaturated, right? We can't break them all up. That's fine. But we're not talking about that. We're just talking about simple, you know, a few grains of sugar into a cup of water. They're going to dissolve. They're going to break apart. They're going to undergo that process of separation. Okay? Look, in here, do you see any positives or negatives in that molecule? The answer is no, there isn't any. Therefore, they do not conduct electrical current, right? We talked about that in the first slide. Molecular compounds do not conduct electrical current. They're called non-electrolytes, okay? Now, we're going to move on to the next one here. The next one here is called soluble ionic compounds. And the process that it undergoes, or the term that you need to know, is something called dissociation. Dissociation, soluble ionic compounds. Okay? Undergo a process called dissociation. Let's see here. I'm going to, no, let's go back here. When you take sodium chloride, which is an ionic compound, so we're going to switch gears. Molecular, that was last sheet. Today, now we're going to look at ionic here. Ionic compounds, they are, like I said, the term that goes with that is dissociation. When you put an ionic compound into water, it'll do two things. And technically, I only have one example. Well, I actually kind of do have two examples here, but it'll undergo two different possibilities here. Sodium chloride solid, when you put it into water, we need our periodic tables out today too, by the way, guys. So let's get those out. We're actually going to use these quite a bit here today, so might as well grab one now. Yeah. Grab one if you don't have one. We're going to find, we'll find chloride across the top, okay? So when you're looking at the solubility chart, usually you find the negative ion across the top. So I look across the top, oh, there it is, chloride, okay? There's chloride, and then I say, okay, where's Na plus going to fall into, because it's an ionic compound, of course. Well, Na plus, is it in the most category, or is it one of the ones listed in the bottom column there, bottom row? And the answer, of course, is it's not listed at the bottom, so I guess it must be in the most category by default, okay? So since it's in the most category, okay, we know that this is going to be a very soluble compound, very soluble. And because it's very soluble, when you put sodium chloride into water, very soluble implies that it breaks up very well, okay? So we're going to get a lot of sodium ions and chloride ions, a lot, okay? Now, this is kind of an analogy, and this is maybe not exactly what happens, but I want to show you the difference, because there is two parts to this solubility chart here. If I took 100 NaCl's, let's say, or you could take 1,000 or whatever, but I'm just going to keep it simple. Let's say I just took 100 of them, and I put it into a beaker. Generally what happens is, almost all of them break up. In fact, if I just took 100, I'd probably be pretty confident that all of them break up. So these are just some numbers I'm kind of throwing out there. It's probably not exactly what happens, but roughly speaking, you would say out of 100, about 99% or 99 out of 100 would kind of look like that. Okay? So almost all of them break up. In fact, probably in most cases, they probably all would. A few, one in this case out of 100, may actually stay together. In other words, may actually not break up. Now that depends on a lot of things. It depends on temperature of the water, how soluble it is. This is just a very general chart, okay? Very general. It's basically, it's soluble in water, it's not. We don't know the degree. In other words, there could be two compounds on here that are both very soluble, but have very different degrees of solubility, okay? It depends on where the cutoff is. There's a big book on it, if you're ever interested. Well, yeah, about this big. And you can look up the solubility of each ionic compound, exactly what it is at a specific temperature kind of thing. So out of 100, I'd say about 99 probably break up for sure, and about 1 maybe doesn't. But majority break up, and in fact, if not all. This also, by the way, there's always an equilibrium inside of these beakers. So what happens is there will be an equilibrium. So this eventually would break up into something like this, and maybe one of those might join back together. Okay? And we'll talk a little bit more about the equilibrium later. But generally speaking, that's what happens. In this particular case, this process is called dissociation, where the ionic compound breaks up into ions. Now, if you look here, do you have a lot of pluses and minuses in this beaker? Yes, you do, right? So I would expect that this to be a very good electrolyte. Very soluble, right? Very good electrolyte. Conducts electricity very well, okay? So, those are all important things to know about that. Yep. Because it's sodium ions, mostly. Just gives it that sodium. Yeah. Now, when that's a very soluble ionic compound. What happens with the ones that aren't very soluble? So that's the bottom row here. It says actually slightly soluble. What happens with those? Well, it's kind of similar still, but a little bit different as well. Okay? I just want you guys to understand that, you know, if we took calcium sulfate, for example, I really should have put this on a different page perhaps. Let me just put a little division here. If I take some calcium sulfate, well, find sulfate, you remember, guys, when you're looking at the chart, look across the top for the negative ion first, okay? Always look for the negative one first. So you find SO4, it's a 2- charge, it's sulfate, of course. And then look down, where does calcium fall? Is it in the top column or is it in the bottom column? And it is where? Top or bottom? On your chart here. Where is it? Huh? I didn't hear. Top or bottom? Where's calcium? Bottom, okay? So it's in the bottom one, right? So here's sulfate right there. Calcium is the first one listed in the bottom column here. So that means that it's slightly soluble. Well, okay, what does that mean exactly? Slightly soluble. Well, it means that if I took 100 of these calcium sulfates and I put them into water, it means that most of them actually probably stay together. Not many break up, okay? So, put this into water, what you end up with is probably a layer of calcium sulfate kind of on the bottom here like that, okay? Calcium sulfate is a solid. We would also call that a precipitate. And it would probably settle to the bottom. It'd probably get really cloudy at first, and then it'd go just sink to the bottom. And over time, it would settle out, and all the calcium sulfate would just sit on the bottom. And the calcium sulfate's white. So you'd see like a white powder that settles on the bottom, okay? However, okay, the thing is it's slightly soluble. What that means is that some actually will break up, okay, but most of it stays together. Yep. Sorry, out of about 100 of these here, 99% would probably stay together as calcium sulfate. So it actually stay together. What happens is water's not really strong enough to pull that compound apart into its ions. So it would stay together. 99%, probably 99 out of 100. However, you will get, obviously, a few ions that will be floating around in here. Okay? Once again, there is an equilibrium thing, and I would say only about 1%. Not very many. So only about 1% break up. Okay? So the thing is, and once again, these are rough numbers. Okay? In some cases, you might get as much as 10% breaking up and 90% staying together. Okay? There's got to be a cutoff somewhere, so I'm just kind of being very generic here. All right? Now, is this one going to conduct electrical current, is the question. Is there pluses and minuses in there? Yes. Is there a lot of them? No. So it will conduct electrical current. It's not going to do it overly well. Okay? So ionic compounds, generally speaking, are electrolytes. Okay? They conduct electrical current, but there's a very, very different vast amount of how much they conduct. Okay? We got a lot of conductivity, not very much at all conductivity. Okay? So we would say here a poor electrolyte. Okay? For calcium sulfate, because not many break up out of that 100. All right? So there is some distinctions even within ionic compounds. All right? That's also going to be important for the next one that we're going to do here. All right? One last thing here about ionic compounds. We're going to talk about right here, bases. Bases are ionic compounds that contain the hydroxide ion. You will need to know that this unit. Okay? We're going to spend a lot of time on acids and bases on the second half here of this unit. And all bases form hydroxide ions, OH minus ions. All right? When bases dissociate, whatever kind of base it is, you will get hydroxide ions, and those hydroxide ions are the things that turn, for example, litmus paper blue. Okay, they're responsible for things like pHs higher than 7, kind of thing, right? 7 to 14 are bases, so they're higher than 7. Things like that. Okay, so bases belong in this same category. Bases undergo dissociation as well. They belong to the ionic compound. Okay, so we really only need to worry about two things so far: molecular compound separation, ionic compounds dissociation. The next one that's special, or has its own category here, is acids. Okay, acids are kind of unique. That's why we name them a little differently. Acids are molecular compounds. Okay, acids are molecular compounds. Think about it. HCl, that's an acid. Okay, H2SO4. Think about all the elements that are involved in H2SO4. Those are all nonmetals, all sharing electrons. Okay? However, when you put them into water, they undergo a process called ionization. Acids and ionization is the term to go with acids. Okay? What does that mean? Well, it kind of says it in the word, right? Acids are molecular compounds that when you put them into water, they ionize, they turn into ions. All right? So acids separate into individual molecules and ionize into positive hydrogen ions, always, and then the negative anion. Okay? If you think about it, right? Look, HCl. If I asked you to draw me HCl, hopefully, most of you guys would show me this, right? You'd say H, this is unit 1. Correct? Molecular compound sharing electrons. Yes? So you would draw me that. That's what I'd want to see. Well, that's hydrogen chloride. All right? In fact, you could even say this. Remember this now? True? HCl. Partial negative. This is a dipole. A polar molecule. Guess what though? When you put it into water, water's also polar. So it helps pull those two apart from each other. Okay? Since water's polar, and this hydrogen ion is a big deal when we talk about acids, it pulls those ions apart, and it pulls those two atoms apart and gives you this here. Hydrogen, which is responsible for pH stuff. Okay? Acids. Really, what is pH? pH is a measure of how many hydrogen ions you have in that solution. That's what it does. When you put a pH meter in, it actually counts up the, basically kind of counts up the ions of H+, and it measures them, and it changes that into a pH, which is what we're going to do in this unit. Okay? pH, so acids less than 7. The more H+ you have, the more acidic it is. The more acidic it is, the lower the pH is, yes? Okay? So it's possible to have acids like pH of 1 and 0 and lower. Yeah. Pure hydrogen ions? Well, pure hydrogen ions, what do you mean? Like just H+? In an acid or just by itself? In water, it's an acid. I don't know by itself. So pH is responsible for those acidic properties, right? Once again, the more of these you have, the lower the pH is going to be. All right? Anyway, so ionization is the process that molecular compounds which are acids undergo. Okay? Acids, once again, can be strong or weak. So, strong acids completely ionize. In other words, they completely break up into ions. Weak acids only partially ionize. So once again, if you were to draw two examples here, HCl, which by the way is a gas, you pump that into some water here. Okay? If you're looking at this, it's very similar to an ionic compound. If you pump in HCl into water, HCl is a strong acid. You'll get about 99% of these, and maybe about 1% here. Okay? You get a lot of free ions, a lot of good conductivity, of course. So very good electrolyte again. For that. Okay? Make sure you guys know there's a difference between strong acids and weak acids, just like, well, ionic compounds, soluble and slightly soluble. If you take a weak acid, for example, acetic acid, vinegar, okay, is a weak acid. If you take a weak acid, by the way, look, if you probably have seen it written like that a few times, right? Why do we write it like that? Well, because technically right now it's a molecular compound. CH3COOH is a bunch of carbons and hydrogens and oxygens. It's a molecular compound. You put that into water, and you will get breaking apart of that compound to form some H+. Okay? So you will get some of this hydrogen and acetate ions. Okay? But for the most part, you will get a lot of, I just put the H in the front instead, a lot of that. 99% here, 1% there. Okay? It's kind of like your weak or slightly soluble ionic compound. Okay? So 1%, 99%. Once again, does it conduct electrical current? Sure it does. Is it good conductor? No. Okay? It is a poor electrolyte. And once again, I'm just making these numbers up, okay, just to give you an idea. But that's the difference between strong acids and weak acids. Strong acids will completely ionize, completely break up, completely. Weak acids partially ionize, okay? Only some do. If you had equal concentration, so if you had an equal amount of hydrochloric acid and acetic acid, and you had a choice to put your finger in one, you would pick acetic acid because there is less hydrogen ions, which is responsible for acidic-like properties. Okay? When you put your finger into the acetic acid, you're mostly putting it into CH3COOH, okay? Which is not as reactive, of course, or as dangerous to you as putting your finger into HCl. HCl is completely H+, which gives you complete properties of pH stuff, right? H+ ions. So these two, of course, what's the difference in pH levels between these two? It varies, obviously, but you can figure that out, and that's something that you'll actually do in Chem 30. You'll figure out the difference between these two as far as how much they actually break up, and you'll figure out the pH based on that. Okay? I can tell you, though, whatever, if you had equal ones of these, this would obviously be a lower pH because it's more acidic. This would be higher, safer. Okay? Can you make those two pHs the same? Oh, sure you can. That's not an issue. I could just dilute this one a lot and keep this one full strength. Okay? So there is obviously, weak acids are still dangerous, but, okay? Strong acids include the following. You need to know this as well. This is still on the same page there. There's only 3 listed here. I'm going to give you another 3 later on, so you might as well study these 3 for right now. Sulfuric acid, which looks like that, okay? Nitric acid, looks like that, and hydrochloric acid, which looks like that. So far, those are your 3. There's another 3 to come later on. There is only 6 strong acids that we classify as strong. 6, that's it. So if you know the 6 strong, you do not have to worry about the weak. There's lots of weak acids. There's only 6 strong ones, so you have to know the 6 strong. And so far, I've only given you a list of 3, so that's, just know that for now, okay? We'll get to the other 3 later on. So, if it's not strong, it's obviously weak, all right? We're going to take a quick break. All right, here we go. So listen up. What kind of reaction is this one right here? Demonstrate the mixing together of lead-2 nitrate and potassium iodide. What kind of reaction is that? Huh? Double replacement, yes. Somebody knows Science 10. That's good. Double replacement. What actually happens in a double replacement? You switch, what have you guys been told? Double replacement reaction, you got to switch the... Okay, that's scary. Huh? You got to switch the metals, right? Well, why do you switch to metals? I don't know. That's what they told me, right? What does it matter, right? Well, here's what's really going on. When you take a double replacement reaction, we're going to take 2 beakers here. We're going to mix them together. In this first one, I'm going to put some lead-2 nitrate into water. That's what that means, aqueous, by the way. It means it's been put into water, right? 2 solutions, lead-2 nitrate solution. I'm going to mix it with a potassium iodide. Get your periodic tables out. On the back, I want you to find lead-2 nitrate. Where is it?
Right there.
Lead-2 nitrate. Shh. It is very soluble, yes? So nitrate is in the very first column at the top, on the left. Very first column. Where's lead-2? Well, it's not one of the ones listed at the bottom. So it's got to be in the most category in the top. Therefore, it's very soluble. What happens with very soluble compounds? We get this, right? True? True. Yes? So we get a lot of those ions, right? Let's say we take 100 of them, we get 99 of them. We get lots. A lot of those lead-2 plus ions and a lot of lead nitrate ions, right? Let's find Ki. Let's put some Ki into a beaker, potassium iodide. So find iodide across the top. Do it now. Find I minus across the top. Always look for the -1 first if you can. Find I minus across the top. Find K plus. Where's K plus? Is it in the most category or is it somewhere listed at the bottom there? It's in the most, right? So in the most category, once again, very soluble. When I put potassium iodide into there, I get a lot of K plus and a lot of I minus, yes? So I get a lot of free ions. Now, we're going to mix these two solutions together. Really what you're doing, by the way, is you're mixing a lot of ions together, right? You're not even really mixing, yeah, you're mixing ionic compounds together, sure. But really you're mixing the ions together, technically, okay? And we're going to mix them together into one big pot here. So we're going to get some lead 2 plus, K plus, K plus. You can have more of these, of course. I'm just keeping it simple. Nitrates and nitrates, let's say. I don't know. I lost track of how many I need there, but whatever. Okay? You got lots of these ions floating around in there. What do you know about ionic compounds? Look at, there's charges on them. What do you know about that? Yeah. Opposites attract, sure. So opposites attract. Is K plus, that's a plus, is that attracted to nitrate? Sure it is, right? Opposites attract. Do they stay together is the question. Look up potassium nitrate. Potassium nitrate is very soluble again, right? So what happens? Sure, they might come together, but water's strong enough to break them apart again. Okay? So they might come together, but if you had 100 potassium nitrates, most of them would be ions, yes? Okay? Very soluble. Potassium and nitrate's very soluble. What about potassium and iodide? Are those two still attracted to each other? Well, sure they are. Do they stay together, though? Well, once again, you looked up potassium iodide, you told me it was very soluble, so they split apart, yes? They stay apart from each other. Yeah, they're still attracted to each other, but they're not strong enough to stay together. Water's strong enough to break them apart, okay? What about lead 2 plus and nitrate? Are those two opposites attracted to each other? Oh, sure there is. Okay? But look, once again, lead 2 nitrate is very soluble. So they're going to remain apart from each other. Okay? That doesn't mean that they don't come together, and maybe one or two stay together, but the majority of them, when they come together, they will break up again, just like I showed you earlier, because it's very soluble. Water's strong enough to pull us apart. Finally, look, lead 2 plus and iodide. Look that one up. What do you see? Well, you find iodide across the top. Where's lead 2 plus? It's in the bottom, right? That tells you that it's slightly soluble. So will those two come together? Sure they will. Are they going to stay together? They actually probably will stay together because they are slightly soluble, which implies that if I had 100 of those come together, about 99 of them probably would stay together. Okay? And when they come together, there's a very good chance that they're going to be denser than water. They're going to form a solid, which we call a precipitate. And that precipitate will fall to the bottom usually. Okay? So you will, in fact, see lead 2 iodide solid form at the bottom. Okay? And that's really what happens in a double replacement reaction. It is a bunch of positives attracted to a bunch of negatives. Some stay together. Most of them probably don't. Okay? You might say, well, why did we, we can talk about why is the potassium ions even in there then? What's the point of that? Or the nitrates or something like that. And we'll talk about that. That's going to be actually a lesson, Unit 4 topic. Molecular ionic net ionic equations, what actually happens in that. So we'll come back and review that a little bit. But that's actually what takes place in a double replacement reaction. You get, usually in a double replacement reaction, you get a solid, okay, and another thing that just kind of floating around in there. So really, what do you get from this? Well, you get some lead 2 iodide solid, and you get some potassium ions, and you get some nitrate ions, technically. Now, once again, what does that really look like? Well, like I said, you get a bunch of solid at the bottom, and then you get a solution of potassium and nitrate ions just floating around on top of there. Okay? That's really what you get. Okay? So if you actually looked at this beaker again here, well, let's maybe move it up a little bit, you would actually get, like I said, probably a chunk of lead iodide here, and you get some K plus and nitrate, aqueous, okay, in your water there, and they'd be floating around on top there. Okay, and that's really what takes place in a double replacement reaction. Why do we write it like that? Why do we say metal switch places? Because they kind of usually do, I guess, in a way. It's a simple way of saying that. They don't always, but they usually do. And this is really what you get from that. We write this because it's easier for us to balance, etc., and do other things with that. That's why we write it like that. But we'll talk about that a little bit more in Unit 4. Okay? Any questions on that? Yeah, okay. So, knowing that basically positive ions and negative ions combine together to give you a solid, okay? And then that's something we could see, right? If you actually looked at this beaker, what would you see? You'd probably see a bunch of water up here, okay? What looks like water would be clear, because potassium ions and nitrate ions don't have a color to them, okay? You'd probably see a bunch of clear water, and then you'd see probably lead usually has a yellowish color to it. So lead iodide at the bottom here, a yellow precipitate stuck along the bottom. That's what you would see physically. You can see the lead 2 iodide. You'll actually see it happen. We're going to do double replacement reactions eventually here. I know you probably did one in Science 10, but we'll do another one. It's fun. It's always cool. We got a couple neat ones for you. All right. So you'd actually see this form. Well, gee, if I had a beaker full of ions, could I use that, or could I use my knowledge of the periodic table, the solubility chart, to determine what's actually in that beaker? So that's what we're going to look at next here. Okay? It's something called selective precipitation, and really it's just kind of more practice with your solubility chart, if nothing else here. So let's take a look at the first one here. If I had a beaker here, let me put this a little farther down here. So here's your first example. How could you test? Let's say I put a beaker down and I say, hey, test to see if there's bromide in that beaker, Br minus. You would say, well, okay, I can't see anything right now because I'm just looking for that one ion. What could I add to the beaker that would help me determine whether bromide's in there or not? What would you want to add? Kevin? What's that? Right, so pick one there. Sure, lead 2 plus, copper 1 plus, Ag plus, mercury 2 plus, that's a special one there, or that's thallium, by the way, at the bottom there, Tl plus. Any of those you could add to test for that. Okay, now there's a problem with this, so I'm going to ask you to kind of think about that as we go along here. But if I added, let's say, I'm going to add just, let's say, some Ag plus. So find Br minus across the top, Br minus across the top, and look in the bottom part. You'll see that there's an Ag plus down there. That would make it slightly soluble or a precipitate, and the precipitate is something I can visually see. Okay, so I'd say add Ag plus to test for the bromide ion. Two things can happen, by the way. Okay, so I put the beaker down and I say, tell me, is there bromide in here or not? Well, those are your two options. There could be bromide in that beaker, but there might not also be bromide in there. Maybe it's just a glass of water. So if you get a precipitate, so if precipitate forms, then Br minus obviously was in there. We say Br minus is present. Okay, so if a precipitate forms, I would tend to believe that bromide is present in that solution, okay, in that water. This is what conductivity, or not water meter, or not water meter, water testers, water kits that you buy to see what kind of minerals you have in your water, like copper or magnesium or whatever. That's what these basically do for you. Same kind of, based on the same kind of principle, basically. Okay. If no precipitate forms, then I guess Br minus is absent, right? Because if there's no Br minus, what does the Ag plus react with? Well, probably nothing in most cases. All right? Like I said, there is a problem with this type of test here. And we'll do one more here, and I'll see if you guys know what that is. But those are kind of your two possibilities, okay? Maybe I just give you a beaker of water on one side and maybe a beaker on the other side. One's got bromide, the other one doesn't. You add some Ag+, one would form a solid, the other one wouldn't, okay? How could you test for the presence of magnesium in a beaker here? So let's say you had a beaker here, Mg2+. Maybe it's there, maybe it's not, I don't know. What could you add to test for magnesium? What could you add to test for magnesium? Sure, fluoride. Now, once again, when you go to do these ones, they're a little bit trickier. You're not going to find Mg2+ across the top because those are all just the negative ions across the top. So you're actually going to have to go down to the bottom here and find Mg2+ somewhere along the bottom, yes? Okay? And the first one that you'll see is, yes, fluoride. It's listed under fluoride. Did you have to use fluoride? No. You could have used, another one would have been, well, probably hydroxide, OH- would have worked. Iodate, IO3 or OOCCO2- would have worked. Carbonate, phosphate, and sulfite, those all would have worked as well. Okay? Obviously, though, remember you always have to add the opposite ion, because if you add another positive ion here, they're never going to react. Never. Okay? So you want to add an opposite ion. She picked F-, that's fine. You're going to add some maybe F- or hydroxide or carbonate, whatever, to test for magnesium. And once again, two things are going to happen. You might get a precipitate. So if precipitate forms, then Mg2+ is present. If no precipitate forms, is absent. Okay? Just right there. Those are your two options. All right? What is the problem with this, what I'm doing here? Anybody come up with a problem? What could potentially happen with any of these, for that matter? Take a look at the solubility chart. Take a look at what we're doing. Take a look at the last one. Magnesium, if there's magnesium 2+, I'm going to add F-. So let's say I add F-. I get a precipitate. What's the problem? Yeah. It could be any of them. Okay? So if you look under F-, you come up to a beaker and you're like, hey, I'm going to test for magnesium. I add F-. Well, the question is, you get a precipitate, and you're like, yay, I got a precipitate. Magnesium's present. But then you find out, oh, actually it wasn't magnesium because lithium and fluoride make a precipitate. Calcium 2+ and make a precipitate. Strontium, barium, iron 2+, mercury 2+, and lead 2+. All those make a precipitate with F-. So the question becomes, okay, so I add F-, but how do I know it was actually magnesium in there? What if it was calcium? You know, I say, here's a beaker, test for Mg2+. And you put the F- in, you get a precipitate, and you're like, yes, magnesium 2+. And I was like, psych. That's what we used to say back in the old day. Psych. Okay, that's old. Okay, it's actually calcium. Fooled ya. Ha ha. But that could happen, right? And so this test is really limited, right? I mean, you have to do it under controlled circumstances. You can't just walk along. You know, you're going home from school today. You're walking like me. Hey, you go like, hey, look, a beaker of water. I wonder, does it have magnesium in it? Because this happens to me sometimes. And I'm like, I wonder, could there be Mg2+ in there? Oh, let's get the tester out. So I get the tester out, and I got some, here's some fluoride. I dump it in. Yahoo! Right? I'd have no idea that that is actually magnesium in there. It could have been the calcium, it could have been the lithium, it could have been strontium, it could have been any of those other ones in there. So the answer is, if I did that test, what would I know? I would know that one of those ions is in there. Good for me. Would I be able to test magnesium? Probably not. Unless magnesium and fluoride make a special color of precipitate, unless I have other ways of testing it, I'd really have no idea. Okay, so this is really just to kind of get you used to the periodic table a little bit. It does narrow it down for you, for sure, because it narrows it down to those ions. After that, you could do things like flame tests, all right, and things like that. So it does narrow it down. It's not the best.